We can photograph the birth of galaxies billions of light years away and track asteroids speeding through the dark. Yet the most stubborn mystery in modern science isn't out there in the cosmos. If you zoom back in from the edge of the universe, past the clouds and straight down to the ground you stand on, you hit a wall. Humanity is effectively blind to what exists more than a few kilometers beneath our own shoes. It isn't for a lack of trying. The Kola Super Deep Borehole represents our most ambitious physical attempt to burrow straight down toward the center of the Earth. But as the drill bit chewed deeper, the rock didn't just get harder. At extreme depths, blistering heat and crushing pressure made the crust behave like plastic, collapsing the hole as fast as machinery could cut it. Today, the project sits completely abandoned. The facility is a crumbling concrete ruin, standing as a permanent monument to a physical limit we cannot cross. After 20 years of drilling, they managed to scratch 12 kilometers deep. To reach the actual center of the planet, you would need to cut through another 6,300 kilometers of solid mass. Since our deepest drills barely penetrate the Earth's outer skin, scientists had to find a different way to determine the planet's internal anatomy. If we can't build a machine to survive the journey down, we have to wait for the deep Earth to send information back up to us. We get that information from destruction. When a massive earthquake strikes, it blasts an immense pulse of kinetic energy straight down into the core. This energy travels in two distinct forms: fast-moving compressional waves called P waves and slower rolling shear waves known as S waves. For a brief moment after a major fracture, the entire planet rings like a giant bell, and those seismic waves are the vibrations traveling through the rock. This monitor shows a global seismic network. To hear that planetary ringing, researchers rely on this vast web of listening stations positioned to catch the waves as they exit the far side of the Earth. These stations use highly sensitive seismographers to record the precise millisecond those vibrations arrive, tracking both their speed and their intensity. When scientists started comparing the data from different continents, they found that the waves weren't traveling through the Earth in straight lines. The paths were bending, a process called refraction that only occurs when waves hit materials of different densities. This confirmed the interior is composed of distinct layers rather than one uniform mass of rock. By measuring where a vibration surfaced and how long it took to get there, we found the first indirect physical proof of hidden structures locked deep underground. Evidence for a liquid core appeared when sensors opposite the globe listened for the earthquake's echo and found the S waves had completely vanished. This gap is explained by a rigid law of physics. S waves ripple through solid rock, but they cannot travel through liquid. By tracing exact angles where these shadow zones began and ended, geologists mapped the precise depth, thickness, and density of these hidden layers. This provided the first complete map of our planet's interior: the thin crust, massive mantle, liquid outer core, and solid inner core. We didn't need to dig thousands of kilometers. By tracking the shadows of earthquakes, we discovered a hidden ocean of liquid metal spinning at the center of our world. Human ingenuity mapped a region over 6,000 kilometers deep using nothing but raw physics and patience. With the geometry of the interior finally defined, it is time to examine the specific characteristics of each distinct environment. Let's step off the surface and descend into the first, thinnest, and most fragile layer of all, the shifting crust beneath our feet. When you stand on a mountain or look out over a city, the ground beneath your feet feels permanent. It's easy to assume that everything humanity has ever built rests on a massive foundation of solid rock, extending straight down into the planet. In reality, if you were to shrink the Earth down to the size of an apple, it's significantly denser. This shell is shattered into dozens of jagged puzzle pieces called tectonic plates, which float side by side across the globe. These plates move at roughly the speed your fingernails grow, only a few centimeters each year. Over millions of years, that persistent drift pulls continents apart and reshapes the entire map. Everything we build rests on a fractured shell, drifting across a volume of rock much larger and more powerful than the surface itself. Directly beneath that thin crust lies the mantle. This layer makes up 84% of Earth's total volume, acting as the primary driver of our planet's geological activity. To cross it, you would have to travel nearly 2,900 kilometers through the interior before reaching the next layer. While the mantle is mostly solid, the intense internal heat changes how rock behaves at this scale. Under these conditions, the rock becomes pliable, allowing it to flow and churn like a highly viscous liquid. This heat creates convection currents. Superheated rock near the bottom expands and rises toward the crust, cools off, and sinks in a continuous loop. Moving horizontally, it creates immense friction against the crust, acting as a planetary conveyor belt, gripping and dragging tectonic plates. This churning engine deep underground is responsible for every drifting continent and spreading ocean floor on the surface. Heat and upward pressure from the mantle constantly probe the drifting crust above, seeking out structural weaknesses in the plates. When pressurized magma forces its way through these fractures and violently breaches the surface, a volcano is born. Magma isn't the only source of tension. At the boundaries where tectonic plates meet, the mantle's movement forces massive slabs of rock to grind against one another. These plates frequently catch on one another, locking together while the mantle continues to push from below. When the rock finally snaps, it releases decades of stored energy in the sudden jolt of an earthquake. Earthquakes and volcanic eruptions serve as the exhaust systems for the planet, venting the intense heat and mechanical tension generated by the mantle's engine. Descending past the mid-mantle to its lowest reaches, temperatures rise to 4,000 degrees Celsius, hot enough to melt most metals instantly. The weight of the thousands of kilometers of rock above creates such immense pressure that standard physics begins to warp. Here, rocks are forced into dense crystalline structures that cannot exist under surface conditions. Eventually, the solid mantle hits a hard limit, transitioning into an entirely different state of matter. Directly beneath the solid rock of the mantle sits a churning ocean of liquid metal. At this intersection, we find the source of the mantle's heat and the origin of the magnetic field protecting life on the surface. To see how that works, we have to descend into the liquid outer core. Take a look at this animated diagram. If Earth were the size of an apple, the crust, the only part of the planet we've ever actually lived on, would be proportionally thinner than the apple's skin. Beyond that paper-thin layer is an immediate drop-off into the freezing, empty vacuum of space. That void is highly active. Our planet faces a constant bombardment of radiation and supercharged particles fired directly at us by the sun. When those solar winds hit orbital infrastructure, the intense radiation can short out satellite electronics, disrupt global communications, and instantly knock out GPS networks. The only reason those particles are not currently stripping away our atmosphere and reaching the surface is a massive invisible magnetic force field surrounding the planet. Since we cannot physically drill past our incredibly thin crust to see what is generating the shield, our survival depends on a hidden deep Earth engine that we cannot physically reach. To find the source of that magnetic field, we have to drop straight down through almost 2,900 kilometers of solid, crushing rock. At that depth, we hit a hard transition line. The solid rock of the mantle abruptly ends. The solid rock finally gives way, revealing a vast, violently swirling subterranean ocean of superheated molten metal directly beneath us. This is the outer core. It is made almost entirely of liquid iron and nickel, and it boils at temperatures exceeding 5,000 degrees Celsius. This deep, superheated ocean of churning metal is the actual generator creating the magnetic force field high up in our atmosphere. Take a look at this cross-section diagram. As liquid iron physically swirls around the center of the planet, the movement acts like a massive dynamo, generating the expanding magnetic field lines you see pushing outward. Pushing past those swirling liquid currents to the absolute center, we hit another hard transition, the inner core. Temperatures match the sun's surface, yet this massive iron sphere is completely solid. This happens because of extreme planetary pressure. The sheer weight of the entire planet pushing down compresses the iron atoms tightly together that they physically cannot transition into a liquid state, regardless of the intense heat. Everything living on the surface relies on this highly specific standoff deep inside the planet. a delicate balance between crushing gravity and extreme thermal heat. That solid inner core and the liquid outer core surrounding it are locked in an ongoing chemical and thermal reaction. Over vast stretches of time, the liquid outer core is continuously, very slowly losing heat. As temperature drops, tiny fractions of liquid iron crystallize, freezing onto the inner core and adding new solid layers every single year. This steady, hidden crystallization process releases energy, physically driving the molten currents above it. It acts as a steady planetary heartbeat, keeping the fluids moving and the magnetic shield active. This diagram shows the entire planetary machine working in sequence. The solid inner core grows, forcing the liquid outer core to swirl, generating the magnetic field. That deep engine powers the force field, successfully deflecting intense solar radiation away from our fragile atmosphere. No human, probe, or camera has ever traveled deep enough to witness any of this happening. Researchers deduced the mechanics of this subterranean world entirely through mathematics, analyzing the exact ways that seismic waves echo and bend as they travel through the planet. By using physics to decode those deep vibrations, we gain the ability to accurately map a massive subterranean engine we will never physically reach. The ground beneath our feet is actively moving. It serves as the thick outer roof over a dynamic, ever-changing metallic core. From the absolute center to the edge of space, every layer of the Earth works as an interconnected system to sustain life. To understand exactly how we decoded those underground echoes, click on the next video to see how the devastating power of earthquakes provided the data to map Earth's hidden core.